Hi everyone, I'm Isha Andaria. I work for Dr. Botina Manasra at Department of Physics, University of Arkansas. And the main aim of this project is to correlate different electronic structure calculation methods with the output thermoelectric performance of bulk materials. So the thermoelectric generator operates on a simple principle of Seebeck effect, which is nothing but conversion of temperature gradient directly into DC voltage. And this conversion efficiency depends on the thermoelectric figure of merit Zt, which is given by S square sigma T upon kappa, where S is the Seebeck coefficient, sigma is the electrical conductivity tensor, and kappa is the thermal conductivity tensor. So the most important parameter that we gain from any electronic structure is the band gap value Eg. And as you can see, all the three quantities S, sigma and kappa depend on Eg in different ways. Now, when it comes to the DFT calculations of electronic structure, the most challenging quantity is known as exchange correlational potential VXC. And the first approach that I use for accounting this VXC is known as generalized gradient approximation using the PBE functional. But it doesn't account for the correlation effects, and even the Vx that it gives is incorrect. Hence, the band gap we obtain is severely underestimated. So the next option is to use meta GGA or sometimes even hybrid functionals. I use modified Becker-Jones potential, which corrects this Vx, but still there is no account of Vc. So we use the GW effect, which accounts for the Vc as well. Here G stands for Green's function, which takes into account the excited state properties of an electron, and W is the screen Coulomb potential, which takes care of the correlation effects between an electron and electron. However, when we perform this actual calculations, it is computationally very expensive. It requires a lot of SUs, and the parallelization itself is difficult because the operator that is used for this GW is non-Hermitian, non-local, and is also a function of the energy obtained from the Contram calculations. Another important thing is that since we are aiming for a quantitatively correct band gap value, we have to converge the results with respect to k points, number of unoccupied orbitals, as well as the screen Coulomb interaction cutoff, and this makes the computations even more costlier. So I have used a full electron potential core Win2K, and as you can see the diagram over here, this is the electronic band structure of indium sulfide. Blue lines are the ones obtained using modified Becker-Jones potential, and red ones are obtained from GW. And if you look at the last or the first conduction band, you can see that there is a direct splitting. And this is showing that there are qualitative differences to the band structure as well. And these things will have drastic impact on the thermoelectric Onsager coefficients that I will calculate further using Boltzmann transport theory and deformation potential theory. Thank you.